Now we're going to think about momentum, and momentum-related ideas are very closely associated, as you'll see, with stuff we already know about forces and accelerations. Start with a definition. Momentum is a vector. It's just equal to mass times the object's, times that mass's velocity. And it points in the same direction as the object's velocity. That's what this equation tells us. This vector can be equal to this vector only if they point in the same direction. So just as an example here, let's imagine some objects moving back and forth along a straight line, and that the motion is described by this position versus time diagram. Starts out moving in the positive direction for the first 4 seconds, has positive velocity, and then moves in the negative direction for the next 2 seconds, and then stays at the same location, the x equal 2 point, for a while after that. What's the momentum that corresponds to that kind of motion? Velocity is changing, as this graph tells us, so momentum will be changing. Remember that, go way back to some of the basics, in a position graph, a position versus time graph, slope is velocity. And of course, velocity is one of the factors that we need in order to find momentum. Just to keep it simple, let's say that the mass of our object is 2 kilograms. So we know the mass, so in order to find the momentum, we need to figure out velocity. Velocity is slope. So for the first 4 seconds here, velocity, which is defined as change in location divided by change, the length of time it took to make that change. And of course, this quotient here, this ratio here, is just the slope of this line. Change in the vertical variable, position, divided by change in the horizontal variable, time. And so over the first 4 seconds, the change in location, the displacement, is 8 meters in the positive direction. The object moves from x equals 0 to x equal 8 meters in 4 seconds. So 8 meters per 4 seconds, that's a velocity of 2 meters per second. And then that's what's happening from 0 to 4 seconds. And then from 4 to 6 seconds, do a similar thing. Change in position divided by the length of time it took to make that position, or change in the vertical variable of that position graph divided by change in the horizontal variable of that position graph is slope. And so the change in position, you go from 8 to 2. The change in position is -6. In those 2 seconds, the object moved 6 meters in the negative direction. And so 6 over 2, minus 6 over 2 is -3 meters per second. So those are the speeds, those are the velocities from 0 to 6 seconds. So over the first 4 seconds, the slope is constant, so the velocity is constant at this value of 2 meters per second. And if velocity is constant, then momentum is constant. The velocity was 2 meters per second, and the mass was 2 kilograms, so the momentum is 4 kilograms times meters per second for those first 4 seconds. Then, from 4 to 6 seconds, the motion changes direction. In other words, the velocity changes sign. If the velocity changes sign, the momentum changes sign, because momentum points the same way as the object's velocity. And from 4 to 6 seconds, the velocity was -3 meters per second, a mass of 2 meters per second, or 2 kilograms. So the momentum is 2 kilograms times -3 meters per second. So that's a momentum of -6 kilogram meters per second. But then, at 6 seconds, the object stops. From 6 seconds on, it stays at the same location. In other words, not moving, 0 velocity. And so 0 velocity means 0 momentum from 6 seconds on. Just like that. Okay, now, here comes the most important thing about momentum. Let's play with this equation a little bit. We deal with situations where there are forces. Forces cause accelerations. Acceleration means that the velocity is changing. So if there are forces causing the velocity to change, that means those forces also cause momentum to change. Let's think about change in momentum. Change in anything is the final value minus the initial value. And final momentum is just mass times final velocity. Initial momentum is just mass times initial velocity. You can have changes in momentum that involve changes in mass as well as changes in velocity. For example, when it first leaves the ground, most of the mass in a rocket is taken up by its fuel. As the fuel burns, the grand total mass of the rocket decreases quite a lot. So there's quite a lot of momentum change because of mass change in a situation like that. But we'll just look at the simple situation where the only changes in momentum happen because of changes in velocity. So factor out the m, mass times the quantity v final minus v initial. But of course, final value minus initial value, we always write as delta. Final velocity minus initial velocity is what delta velocity means, and that's change in momentum. Now, just as we were interested in the rate at which position changes, right, that tells us velocity, and the rate at which velocity changes, that's acceleration, we can think about the rate at which momentum changes. Just divide both sides of the equation by the length of time it took to make this much momentum change. Delta t seconds. In delta t seconds, there was this much momentum change. But if there was this much momentum change in delta t seconds, it took precisely the same amount of time to get this velocity change. Look at the right-hand side here. We recognize that. Delta v divided by delta t, that's the rate of change of velocity, in other words, acceleration. Delta v over delta t is just our definition of acceleration. And so now we have mass times acceleration. Mass times acceleration. Newton's second law tells us that that is equal to the net force. So we've got a significant idea here. The rate of change of momentum, and I'll just write this up here for handy reference, we're going to use it a lot. The rate of change of momentum is equal to the net force that an object feels. And here's a simple example of that. Let's say we know the mass of an object and we measure its motion, so we can figure out its velocity at different times. If we know both velocity and mass, we know the momentum. So we're able to make a graph of momentum in kilogram meters per second, mass times velocity, a graph of momentum versus time, and in this example, momentum will change as time goes by. Time in seconds. And let's say that after 4 seconds, well, at time 0 the object was at rest, 0 velocity, 0 momentum, and then it speeds up. Velocity increases, so momentum increases. Speeding up and moving in the positive direction, so positive velocity, positive momentum. And by the time 4 seconds have elapsed, the momentum of the object is now 5,000 kilogram meters per second. And then in the next 2 seconds it turns around and slows down as it moves in the opposite direction until finally, after 2 seconds of motion in the negative direction, it comes to a stop. 0 momentum, which of course means 0 velocity. From that, we can make, from that information, and if we know that the mass is 2 kilograms, just like in the previous example, we can figure out what a graph of acceleration versus time looks like. Time in seconds and acceleration in meters per second. Okay. So what are we doing? We know the mass, and we're trying to find acceleration. So if we know the net force, we can use that plus our knowledge of the mass to figure out the acceleration, just using Newton's second law. Acceleration is net force divided by mass. And we can figure out net force from this diagram here because the rate of change of momentum is the net force. But what else can we say about this rate of change of momentum? Delta P divided by delta T. Delta P is just the, if you look at this graph, it's just the change in the variable along the vertical axis, and delta T is just the change in the variable along the horizontal axis. In other words, delta P over delta T, rise over run, delta P over delta T is just the slope of this line. And that's consistent with something that I've mentioned many times before, a graph of anything versus time. In a graph of anything versus time, slope is the rate of change. So in a graph of momentum versus time, slope is the rate at which momentum changes. Just change in momentum divided by how much time it took to make that change, rate of change. So slope here is delta P over delta T, but that's equal to the net force on the object. So delta P over delta T from 0 to 4 seconds is, well, delta P momentum went from 0 to 5,000. So the momentum change was 5,000 kilogram meters per second increase, positive 5,000 kilogram meters per second. And how long did that take? It took 4 seconds. So, $5,000 divided by 4 is 1,250. Kilogram meters per second. In other words, kilograms meters per second, mass times acceleration, that's force. A kilogram meter per second is a Newton of force. So we have 12,500 newtons for the net force during the time from 0 to 4 seconds. That's the net force. The mass is 2 kilograms. So divide that net force by 2 kilograms and you've got the acceleration. Let's make this situation a little more realistic. Make it 200 kilograms for the mass. So a net force of 1,250 newtons divided by a mass of 200 kilograms gives us 6.25 meters per second for the acceleration between 0 and 4 seconds. Now, for the net force during this time, now momentum is still positive, so velocity is still positive, but momentum is decreasing, which means velocity is decreasing. Positive velocity decreasing, getting less positive. In other words, the thing is slowing down, which means the net force acting on the thing is now pushing backwards, pushing in the negative direction in order to slow it down. And the acceleration always points in the same direction as the net force that caused it, so the acceleration points backwards. Negative acceleration in this case as well. And let's see what those numbers look like. From 4 to 6 seconds, the change in momentum is losing 5,000 kilogram meters per second, a decrease, a subtraction of 5,000 kilogram meters per second. And the amount of time it takes to make that change is 2 seconds. So the change in momentum in this case is 2,500 kilogram meters per second. Or that's minus 2,500 kilogram meters per second, or minus 2,500 newtons. That's the net force between time 4 seconds and 6 seconds. So we'll calculate the acceleration for that by, again, using Newton's second law. The net force in this case is 2,500 or negative 2,500 newtons, and the mass is 200 kilograms. So dividing that by 200, 2,500 divided by 200 is the same as negative 25 over 2, or negative 12.5 meters per second. That's the acceleration from 4 to 6 seconds. Now, let's go back to that equation over there, which we've been using already, and just multiply both sides of that equation by delta t. So we're on the left-hand side, we now have just delta P, and on the right-hand side we have net force times delta T. Remember, this delta T was the amount of time it took to make this much momentum change, but you get that momentum change because there's a net force being applied. So you should also think of this delta T as the length of time during which this force was present. The length of time during which this force was acting on the object so as to give it this much momentum change. This we call the impulse momentum theorem. Sometimes this product of net force and time interval is called impulse. But impulse turns out to be just the same thing as change in momentum. Impulse turns out to be just another name for change in momentum. The algebraic symbol that's often used for impulse is capital J. And impulse just is the same thing as change in momentum. This is actually a physically significant quantity. We encounter it quite often. For example, if you're hitting a tennis ball or a golf ball or a baseball, in all cases, to hit it properly, you follow through after your swing. You don't just stop as soon as the ball makes contact with your racket or club or bat. Why? And the reason why is because of this, the impulse momentum theorem. Whether you're hitting the golf ball or the baseball or the tennis ball, in all cases the object is to maximize the ball's momentum change. And according to the impulse momentum theorem, there are two ways to maximize the momentum change. Either get a stronger force or apply that force to the ball for a longer period of time. And by following through on your swing, you're making sure that your club or bat or racket is in contact with the ball for a longer period of time. By following through on your swing, you maximize the delta T factor. And then that helps you to maximize the change in the ball's momentum. This is also the principle behind airbags. That what happens when you come to a sudden stop is that you lose all of the momentum that you previously had. So an instant before the collision, you've got some momentum in the same direction as your velocity. But then, as soon as that collision has completed, and it takes a very short amount of time, it's not zero time to complete the collision. You come to a stop, your car comes to a stop, not instantaneously, but within a short time interval. So after that short time interval, you no longer have any momentum because you've come to a stop. So your momentum change is a loss of all the momentum you started with. That is, delta P is final momentum minus initial momentum, but the final momentum is zero because you've come to a stop. So your momentum change is a loss of, or a subtraction of all the momentum that you started with. And of course, there are two ways to make that momentum change happen. just as there are two ways to maximize the momentum change when you're hitting the ball. You could either have a really, really strong force applied for a short period of time, or you could get the same momentum change, the same loss of your initial velocity, by applying a weaker force for a longer time. And this latter situation is what the airbag does. By presenting a surface that's just a little bit soft, not all that soft, but certainly softer than the dashboard or the steering column, when you collide with that slightly soft surface, it's got a little bit of give, and it slows you down more slowly. You don't stop instantly the way you would if you hit a hard surface. You squish the surface for a little while, a few milliseconds longer, and so that way the same momentum change can happen with a weaker force pushing back on you, because the force is acting for a longer period of time. When you hit something hard, you come to a stop very suddenly, so that backwards pushing force on you acts for only a short period of time, so it has to be a really strong force to give you the momentum change. Strong force can do a lot of harm. A weaker force will do less harm. You might get some bad bruises as opposed to broken bones. And now, one more idea about the impulse momentum theorem. When some object is feeling an impulse, feeling a short, sharp shock, a force acting on it for a short period of time, sometimes we like to describe that interaction with a graph of net force versus time. And take a simple case where for some short period of time, delta t, a constant force is acting. A constant force with a magnitude that we'll call just plain F. Well, this is the value of the net force for this long, so the momentum change is just that force times that length of time. It's a positive force, so it's going to push you in the forward direction, and so it gives you an increase in your positive momentum. So delta P will point in the positive direction, and that works out perfectly because this force is a positive force, so that's a positive number, and a length of time is just by definition of length, has to be a positive number. But notice also, delta T times F is just width times height of this rectangle between the force line and the time axis. So on a force versus net force versus time graph, area between the net force line and the time axis is numerically equal to the change in momentum, also known as impulse, remember that. And that works not just for this simple case of a constant force, but it works for any kind of positive force, changing in any weird way whatsoever. if we're dealing with a negative force, there's one little extra twist that we have to add in. But basically, in the case of a negative force, again, the area between the force line and the time axis will be closely related to the change in momentum, also known as impulse. So imagine this. Imagine a negative but constant net force acting on an object for some length of time that we'll call delta t. Well, it's still the case, it's always the case, that change in momentum is net force divided by the length of time that net force is applied. In this example, net force is a negative number. Length of time, by definition of length, is a positive number, so the momentum change is negative. Right? The net force is pointing in the negative direction, so it will add negative momentum or subtract away positive momentum, meaning that the momentum change is negative. The momentum becomes more negative because of that negative net force. But net force times time, in this case, is just minus F times delta t, but absolute value of F times delta t is again the area. So F times delta t, where this is just the magnitude of the absolute value of the force, right? The force is negative F. F times delta t is the area. So what we have here on the right side of the equal sign is minus 1 times the area equals the momentum change when the net force was negative. So our rule then would look like this. Change in momentum, also known as impulse, equals minus 1 times the area whenever the net force is negative. Very similar to the area ideas that we had back in chapter 2, where in a graph of velocity versus time, the displacement was very closely related to areas on a velocity versus time graph. Here's an example of all that, how all that might work. And we'll use this version of the area rule. So imagine you're over here, tennis ball is coming at you, and of course the object is to turn the ball around so that you've changed the direction of its velocity. That means you've changed the direction of its momentum. You want, as I said before, you want to maximize the momentum change of the ball. Mass of a tennis ball is about 35 grams. That's about 0.035 kilograms. Since we're measuring momenta in kilogram meters per second, we always want to be sure to use masses in kilograms, not grams. And the ball's initial velocity when it's coming at you is minus 20 meters per second, moving with a speed of 20 meters per second, and we're saying the direction coming at you is the negative direction, so the positive direction is the opposite direction. You want the final velocity to be some positive number. And let's say that while you've got some fancy force sensors on your racket so that you're able to make a graph of net force on the ball versus time. And the force versus time graph turns out to look like this. For the first half of the contact time, the ball is feeling stronger and stronger force, and then feels weaker and weaker force for the second half, but it's always a positive force, which will give the ball more positive momentum than it had before it was hit. And let's see what the numbers are. In this case, the time interval during which the ball was in contact with the racket and being pushed, being hit by the racket. Let's see if I've got the right numbers here. 0.04 of a second. And the maximum force with which the ball gets hit is 80 newtons. Or you could just as easily say that the average force is 40 newtons. But that's all the information we need in order to figure out what the velocity of the ball will be, what the final velocity of the ball will be after you hit it. And for that we use the impulse momentum theorem and the relationship between momentum change and area on the force versus time graph. So we know that momentum change is just equal to the area between the force line and the time axis whenever the force is positive. So let's calculate that momentum change. The rule for area of a triangle is 1/2 base times height. So 1/2 a base of this size, 0.04 seconds, times a height this big of 80 newtons, and so in the end that comes out to 1.6 1.6 newtons times seconds. So we'll call it Newton seconds. Turns out that Newton seconds is equivalent to the normal units for momentum, kilogram meters per second. And now we can use the impulse momentum theorem. Since that's impulse, also known as change in momentum, we can use that to figure out what the final velocity is like after you finish hitting the ball. So change in momentum is equal to the final momentum, which is mass times final velocity, minus initial momentum, which is mass times initial velocity, and pull out that factor of mass. Delta P, we just figured out, was 1.6 kilogram meters per second. The mass of that tennis ball is 0.035 kilograms. The final velocity is what we're trying to calculate, and the initial velocity was minus 20. So we have minus an initial velocity of minus 20 meters per second. So multiply both sides of the equation by 0.03, divide both sides by 0.035 kilograms, and we have on the left 1.6 kilogram meters per second divided by 0.035 kilograms. which gives us 45.7 meters per second. Treat unit labels like algebraic variables, so these kilograms cancel out. And that's equal to, well, remember we divided both sides of the equation by 0.035, so this divides away and all you're left with is that the difference in velocities. That's equal to V final minus 20 meters per second, or V final plus 20 meters per second. That means V final has to be 25.7 meters per second. Or rounded up to 26. So, after you hit the ball in this case, the ball left your racket a little bit higher speed than it had when it was coming into your racket. Speed of 20 meters per second just before it hit, speed of 20 meters per second just after it leaves your racket. So, we'll deal more with impulse in class.